As soon as I finished recording the video for day 5, I kind of immediately realized a cleaner way to do this map transform function that I had written. That even as I was writing it, I was kind of complaining that it felt inelegant and the control flow was complicated, especially this little extra like loop over all the rules and do a thing, but if none of them match, do this other thing. It felt really messy at the time, and I kind of just powered through because this is how I had written it originally. But I want to go back to this and look at another way to write this that I think is just a lot simpler. So I'm going to re-implement map transform, and this takes advantage of a property of the input, which is that we're never going to have overlapping rules. So we don't actually need to change the range that we're matching. We can just match the exact same range over every single rule, and because the rules will never match and they'll never overlap with one another, the same range from the input will never get matched more than once. And this lets us do just a much simpler loop where we don't have this like stack of work. We can just do everything once. So instead, what I'm going to do is say we'll have a list of all of the remaining ranges, and initially the whole thing is a remaining range. And then we'll loop over every rule, and remember that a rule is a range, I did name them, a range, range, and an offset, offset. And what I want to say is when let, and this is going to be matched range, I guess. So when the, call this rule range, intersects with the range that I'm matching, then what I'm going to do is offset it like I did before. So range offset, matched range offset. So that's going to go into an output accumulator just like I had before. Yeah, array push output, and then this matched. And then instead of keeping track of the unmatched ranges, what I'm going to do is subtract away the range that I did match from the remaining ranges. So I'll set the remaining to be mapcat, the remaining. And the function that I'm gonna map cat or flat map or concat map or whatever you want to call this is range subtract the matched range from this thing. So we have the remaining is sort of the unmatched part of the input that hasn't matched with any rule yet. And every time we match a rule, we'll go through and we'll remove bits and pieces of it. And range subtract returns the empty list if nothing matches. So mapcat will like nicely do this. And is that just it? So then we return not just the output, but we'll take the output, splice it in, and then also anything that's remaining, we'll splice that in as well. And now let's test this. And it does exactly the same thing. It's returning a tuple instead of an array, but if you want it to be literally exactly the same, we could return an array, but we'll just take the tuple. It's a little cleaner to me. And yeah, exactly the same function, but without this like kind of inelegant, well, do this, else do that. None of this like loop and nested loop where I don't know, it's kind of hard to reason about this. You break out early every time you match something, but then you might end up still going through every rules every single time, and now you could just have a single loop through a single rule. So yeah, that occurred to me, and I thought it was a lot cleaner. And also, speaking of a lot cleaner, like I had also written this solve function in this really complicated way where I went through each individual element and did the full fold, but of course the type of your input is a list of seeds or a list of ranges, and you can just do this as a single fold, which was what I should have done originally. So that's day 5. But let's get on to today's video. And I'm just skipping day 6 altogether because day 6 is trivial. It's just testing if you know what the quadratic formula is, and there's no parsing at all, so I think that the solution in Janet looks exactly the same as the solution in any other language, so I'm just going to skip it. And I'm going to skip a lot more of the upcoming days because there's, yeah, like I said, not much Janet specific stuff. So let's go on to day 7 because this is a really easy, really fun problem, I thought. And it's the whole problem is just about sorting. And I have some things to say about sorting in Janet that might be interesting. So this is a poker hand. So our job is to figure out what kind of poker hand it is. It looks like this is just a pair. And then this is a bid on that poker hand. And here we have 3 of a kind. Here we have what looks like a 2 pair. So our job is to take all of these poker hands and rank them in order, to like sort them by weakest to strongest poker hand. So let's do it. We're going to parse the input with a peg, so it looks like this consists of a hand, followed by they call this a bid, and I'm going to parse, there's a space in there. I'm going to parse both of these, and then I'm going to stick them into hand 0. I'm just going to give them names. Instead of parsing them as like a tuple like I have been doing, I'm going to stick them into a struct. And hand is going to be just 5 characters. So I'm going to say, I think that number is a word character, so I can just say, like, capture a word, capture a string. But I don't actually want the string. What I want is like a list of all of the characters in the string. And that's kind of annoying. What I want to be able to write is just string split this on the empty string. But Janet actually doesn't let you do that. And I'm going to comment this out for a second just so we can take a look. So string split ABC on comma. That's exactly what you'd expect. Which is give you comma because I mixed up the order of the arguments because I do this every time because it's in the opposite order of string join. So separator first, so it does this split. Now, if you pass it the empty string, I would expect this to just split, between every character that it can, but instead that is an error. So I actually define my own string split like this. So I'll keep core string split, define my own string split, and of course I'll take the separator second, like string split, just one of my least favorite functions in the standard library. And I'll say if the separator is the empty string, then what I'm going to do is map string of bytes over this string. So if you map, we'll test mapping the identity function. If we map this over ABC, you might be kind of surprised by the result. So we get the ASCII byte instead of the string character. And string of bytes will turn bytes into a string. String bytes, what is it? Let's look at the documentation. String, something about bytes from bytes, sorry. In OCaml, everything is of NC. I typed it there. Just saying. Okay, so glad I checked that. So from bytes. Otherwise, we'll just call the core string split function, which takes the sep and the stir in that order. So test that, ABC on the empty string, and ABC on commas. Great. So that lets me write the thing that I wanted to write all along, which is string split on the empty string. So parse a word and then split it into just individual characters. And then the bid will just, as we've done so many times, parse a positive integer like that, non-negative integer. Let's see if that worked. Great, that's exactly what I wanted. So I did not unquote these short funds that I was putting in here. So it replaced it by the quoted abstract syntax tree of this expression, which looks just like that, but I want to actually evaluate and get the function. So unquote, and great. This was just, I don't know, I'll call this like a round maybe, and it is, as it so often is, string split, sorry, got string split on the brain, split on new lines, which this of course takes the separator first, but somehow that makes sense in my head in a way the string split doesn't. Split on new lines around. So that captures all of these, and it looks like they split and are working correctly. So now what we need to do is score them, or sort them. So I'm going to write this solve function now. So I'll take input, and what I'm going to do is sort these. So let's take a minute and talk about sorting in Janet. This back up by the peg. And then test solve, test input, and as always. Great, same thing. Okay, so let's explore sorting. So I'll give it like 4, 1, 2, 5. So the sorted function will return a copy. There's also the sort function, which is in place mutable sort. So I use sorted here. And the way that sorted works is it's not comparator based. You don't give it a comparator function. Instead, you give it a predicate that says, is this before that? So by default, it's essentially the less than predicate. You can give it the greater than predicate to say that larger numbers should come before smaller numbers, and you can use this to reverse the sort order. And this is very cute, but this is really, really bare bones and not very useful. So we really want comparators when we're sorting. And the reason that we want comparators is because we can compose them. And this isn't maybe a very interesting example, but let's say I have points that are like x1, y2, x0, y3, something like this. And I want to say, okay, I want to sort these by x, but there might actually be a tie. I might have like x1, y1. And if x is a tie, then I want to look at y. And I want to like break ties in this way. And if you just have this is before predicate, like you can look at x, see if it's before, but if it's not, you don't know whether that means that they're equal, so you need to break ties, or that it's actually greater than it, so there's no tie to break. So a comparator gives you this concept of a tie. And that's also important if you want to implement stable sort, which Janet's sort functions are not stable because they literally can't be, because it doesn't know how to differentiate ties from greater than. So while I was doing Advent Code this year, I wrote a library to just make this all easier, and I ended up, I think this is the first problem that I wrote it for. We ended up using it a few times, and the library is called comp, just CMP. This is it, and it just gives you functions for sorting things with a comparator-based sort instead of this before predicate-based sort. And they're just comp sorted is just like sorted, except the second argument takes a comparator. And then it gives you a few functions, not very many, pretty simple, a few functions for composing comparators. So given one or more comparators, you can like stick them together, create a comparator that compares on one thing, falls back to another thing, or that does like a nested comparison. If we wanted to compare X on the foo field, we could do this by making a fallback comparison. So let's just try that out right now. So comp sorted, I'm gonna give it this list, and I'm gonna give it, we'll sort by X, and then we'll sort by Y, if it's a tie. And I'm going to use, it's kind of a weird one, but comp import. So normally you'd say like use comp, or you'd say import comp, but by using comp import, what I'm going to do is bring a few symbols in unqualified. So this will give me by, it'll give me then, and I think it'll give me desk. I think these are the only symbols that it brings into scope. Unqualified, and then everything else is like comp sorted, comp each. Everything else gets a qualifier, but like by, then, and desk are simple and short enough, and they don't conflict with anything, that it just brings them into scope. But we could, of course, just import the whole thing and have it all be qualified with a comp prefix. So let's try that out. So yeah, the output is a little bit long. I'm just gonna add a line break. So it sorted it on the X, the value of X, and then it broke ties with the value of Y. And what you can also do is by takes an optional argument, which is once you find X, how do you compare X? How do you compare two X's to each other? And by default, this just uses the built-in Janet function comp, which is the library is kind of named after, which is the integer comparison function. It's not just integers, it's like any native type, so A sorts before B. But we'll basically just use it as our atomic compare. I give it equal types, gives me 0. So this is a comparator function, but you can't use it with any of Janet's sort functions in the standard library. So the default comparator is comp, but we can give it another comparator. So one is desk, and desk is just comp times -1. And when you do that, you get a descending sort. So sort by X descending, and then sort by Y descending, sure. But you can also use this to fall back, like sort by X, and then sort X's by foo. And yeah, if this were like, foo1, etc. Foo0, that lets you like look into a nested structure. And by its first argument can be a function or a keyword. When it's a keyword, it just looks it up in an associative structure. If it's anything else, it tries to invoke it as a function. And the only difference, you can invoke keywords as a function like this, but that doesn't do what you might think it does if you're new to Janet. That tries to invoke X as a method, and it's not a method, so that does not work. Instead, we basically treat it like we said in struct X. Okay, that was a long diversion that didn't really help us solve the problem, but it tells us what we want to do. So we're gonna comp match this, and we're gonna return the sorted output from all of these hands. And the thing we're going to sort by is this hand field. And we're going to sort by hand. We're going to sort by hand strength, I think I'll call it. So by hand, and then by hand strength. And then we also need to break ties. So in the case of a tie, what we do is we look at each card in order. So if you have two pairs, then what you do is you go through and you look at first card, and if they're the same, go on to the second card, compare them until you find one that doesn't match. So we're sorting by hand, and we're sorting by hand strength, and then if that is a tie, we sort by, we'll call this, I don't know, tiebreaker or something, but it's comp each card strength. And comp each will take a comparator for an individual element, and it will lift it into a comparator over lists that will compare each element of the list in order until it finds something that is not a tie. So we've composed this comparator out of these hand strength and card strength functions that we haven't actually written. Another way that's maybe a little bit easier to read is you can just pass multiple comparators to sorted, and it'll combine them as if you'd pass them to then to like create one big comparator. So this is maybe a little bit easier to read, but it's also we duplicate the like by hand thing. So by hand strength, and then if that ties, fall back to by hand, and then this card strength comparator. Yeah, I think actually card strength, I wrote this wrong, really by card strength. Yeah, because this needs to be a comparator, and card strength is going to be a function that just returns an integer. Okay, so let's write these functions. So hand strength is going to be a function that takes a hand, and it's going to basically identify what type of thing we're looking at. So this will be sort of nothing, a pair, two pair, three of a kind, full house, and so on. So what I'm going to do to solve this is I'm going to take, I'm just going to go ahead and look at, I'm going to define this and just say everything is 0, and say everything is 0, just to make sure that it is compiling so I can test it. So this is the very dumb sort function where we just say all hands and cards are equally the same, so we're not really sorting by anything useful here, but we will take hand strength and write some tests for that. So test hand strength, oh my gosh, hand strength of, let's say, a full house, so 3 kings, 2 queens, and let's mix the order up. And what we're going to end up doing here is match the shape of the hand against some pattern. So the shape of a hand, it's another function we can define. Hand shape. And all I'm going to do is I'm going to use this frequencies built-in function. And what this is going to do is return, I'll show you on this. It's going to like count up the occurrence of each element in here. So it said you have 3 kings and you have 2 queens. Great. And that is actually all I need to determine that this is a full house, is that there's a 3 and there's a 2. So I'm gonna actually chain this using this, instead of the prefix notation, I'll use this postfix notation and say hand, give me the frequencies, give me the values, and then sort those so that they're in this ascending order, because who knows what order values gave them back to me in. So that's the shape of a full house. There's 2 of something and 3 of something else. And the only thing that we need to do for hand strength is to say match the hand shape of this hand. And there's a few different hand shapes that we could have. We could have 5. And we'll say, well, let's go in the other order actually. So maybe there's nothing. So we'll say that's a 0. That's the weakest hand you could have. Maybe you have this 2 of a kind. Sorry, this pair, and that'll be a little bit stronger. I think next up is a 2 pair, and I'm gonna just make sure that I'm getting the relative rankings of these correct. So 1 pair, 2 pair, 3 of a kind, where Where does it actually list them? Oh, right here. So high card, all distinct. One pair, two pair, three of a kind. Okay, I had it right. One pair, two pair, three of a kind. Full house. That's our 2, 3. Four of a kind is 1, 4. And then five of a kind. And that's all we have to do for hand strength. And this says 4, which means it's a full house. I guess maybe like a more interesting test is I will give it a list of hands and see that it puts them all in order. So I'll give it a full house. I'll give it a single pair. So 2, 3, 4, king, king. So single pair, two pair, three of a kind. No, that's not a card. And then I'm just gonna sorted by hand strength. Comp sorted by hand strength. Let's edit this just a little bit so I can read this. Okay, and let's test that. The right number of parents. Okay, so single pair, two pair, three of a kind, full house. Okay, so it's working. And then we also need to break ties by looking at cards. So card strength is match card. And what this is gonna be, just case card. 'Cause these are all just literals. So I think it gives me the relative rankings of these, but I think we have a 10 is worth 10. Jack is 11, Queen is 12, King is 13, Aces are high at 14, and anything else is just going to be a literal number, so we'll scan. Number is like the number of int, from int maybe, parse function, so this is like card strength of 2, no there's not a 1 card. Great. Like, obviously that also works. Okay, so now we have this sorted function, and is it working? Let's see. We have a single pair here, which is a 3. Next we have a 2 pair. Next we have a 2 pair, but it looks like it broke the tie correctly because king is higher than 10. These kings match, and then king is higher than 10. Next up we have 3 of a kind, and then finally we have 3 of a kind again, but with a higher card to the start. Okay, so I think it's sorting it correctly. So now what I want to do is the like answer of the solution is to take each hand, each round, I don't know, each of these plays, and we're gonna do a sum loop, as we so often do. And this is gonna be, we'll take the index of the win, and we'll take the bid from it, and iterate over the pairs in. So this is basically like iterate with the index of the iteration. And for each one, what we'll do is times increment I, because rank index 0 is the first rank, multiply that by the bid, and add them all up. So 6440. This example was 6440. Great. So that already worked. With the real input, we get something that looks a lot like that. So I think that worked. Okay. And then part 2 is only a little bit trickier. It's not really very hard, but we can match, do the parsing exactly as we were doing before, except that now J doesn't mean Jack anymore. Now it means Joker. So A lot of this stays the same, but we need a new card strength function. And jokers are now the weakest card. And we need a slightly different, go ahead and make a new solve function. We need a slightly different hand strength function as well, because we have to take jokers into account. So let's look at hand strength. And we'll say, I'll take hand shape as well. Will I? I don't know. Let's make a new hand strength. So what we're gonna do is say, let's look at the hand, but without any jokers. So filter all of the cards equal to J. Not equal. So take all the cards that are not jokers. So we'll pull all the jokers out of it, and then we'll say the joker count is. I mean, we know the length of the hand is 5, but however many we started with, and then without jokers. So that's the number of jokers in our hand, and then you'll notice that. So we want to make the strongest hand possible, but making the strongest hand possible always just means making like given any hand, we would just want to add things on to whatever the most frequent card that we're already seeing is. So if we're mostly seeing kings, the jokers will be kings. And if we're mostly seeing twos, the jokers will be twos, even if there are kings, because all that matters is like the number in the largest position is the best thing that we can improve always about our hand. I don't know if that exactly makes sense, but I'll show you what I mean. So we'll say like most, because we don't even need to say like it's a king or it's an ace. We don't even need to detect what it should become, because we're only going to change the shape. When we're doing the tie breaking, it's still a joker. It's not changing itself. So I'm gonna say largest hand, maybe most frequent card, or like most important card. I don't know. I don't know what the right name for this is, but basically what I want to do is I want to pop the last thing off of the hand shape. Oh, hand shape though is like very no, hand shape works for anything. Okay, so find the hand shape without jokers, and that will give me an array back. And then what I want to do is shape without jokers. I want to pop the last element off. So I'll call this like major card, or like dominant best count maybe. So this is going to be like the single largest number is going to be last. Unless they're all jokers, in which case array pop is going to return nil because there is nothing to pop. So array pop shape without jokers stuff. Best count is this. And then we're going to push back onto this shape without jokers. I should probably just call it shape then. I'm going to put the jokers in it. Array push the joker count plus joker count, best count. And if this is the empty array, then we'll say 0 is our best count. So the joker count will be 5. We could special case that otherwise, but this is like the new shape. And we're always still going to have, one of these valid shapes. And I think I did that right. I mean, I really hate best count. I can't come up with a good name for it, so we could just inline it, just maybe not the best we could do. So let's look at hand strength of, let's say we have a joker, and then we have a 2, a 3, a 4, and a 5. So the best thing that we can become is a pair, which has a hand strength of 1. So that worked. In this case, the joker could become, with the joker, this becomes a 3 of a kind, which has a hand strength of 3. So that worked. What if we have 3 jokers, a 4 and a 5? Well, the best thing that we could become is 4 of a kind. We don't have to think about becoming a full house and like having some of these become 4s, some of them become 5s, because we could just become a full 4 of a kind in this case. Strength 5, and we'll just make sure that our 5 of a kind works correctly, even if they're great, all jokers. That's our hand strength. That's our card strength, and it is otherwise exactly the same solution. So we can even like parameterize this by our hand strength and card strength functions and not duplicate it, but I can do that for this. Let's see if I did it right. 5905 looks good. And over here, that looks right again. So really simple, neat little problem. I had fun solving this one, and I had fun writing comp and dealing with these comparisons. It's just kind of a nice, I don't know, it's nice when you have first class functions and comparators for them. I think this is like slightly more efficient to do it this way. I mean, slightly more efficient, like not in a way that you'd ever notice, but we don't have to look up hand multiple times. It's like we're definitely comparing hand, and then we're just breaking the ties on this one, and I guess it doesn't bring then into scope. Still works. So I guess it's just buy and desk when you use the import thing. So, okay, we're gonna skip the next few puzzles are this, they get very, well, this one's just not very interesting to parse. I don't really like it. I hated this puzzle day. It was probably my least favorite day of all because the solution is so dependent on the particular properties of the input. It's so artificial. But anyway, that's not interesting to parse, so we're not going to learn anything about pegs doing day 9 either. And then we start to get these like grid puzzles that are not actually like things that we would use pegs to parse. It doesn't really make sense. And I'm just going to skip over most of these because they look exactly like, exactly the same they'd look in any other language. So that's it for now.